One of the things Moivre's theorem allows us to do is to play with trig, but using complex numbers. Obviously we know these results, but let's prove it using complex numbers. So we're going to express cos 2 theta and sin 2 theta in terms of cos theta and sin theta. If I think about the complex number cos 2 theta plus I sin 2 theta, we now know that's the same as saying cos theta plus I sin theta squared. Moivre's theorem. If I expand the right hand side out, and now all I've got to do is equate the real and the imaginary parts. So looking at the real part, I get cos 2 theta is cos squared minus sin squared, the result that we know. And looking at the imaginary part, we get sin 2 theta is 2 sin theta cos theta. It's a very quick way of proving those results. Of course, we can push that further. Let's get some results for sin 3 theta. While we're at it, let's do tan as well. The same idea then. Well, cos 3 theta plus I sin 3 theta, I could rewrite as cos theta plus I sin theta cubed. Expand the cubic out, but remembering I squared is -1, so that third term there becomes minus 3 sin squared cos, and that last term becomes minus I sin cubed. And again, equating the real and the imaginaries. Sin 3 theta, there's an expression for it, 3 sin theta cos squared minus sin cubed. It's nice to have the sin 3 theta all in terms of sine. I'll sub in 1 minus sin squared for cos squared, and I get a result, 3 sin theta minus 4 sin cubed theta. Do the same thing with the real parts, and we get cos 3 theta. But that's a mixture of sine and coses. Let's substitute in 1 minus cos squared for sin squared, and we get a nice result for cos 3 theta, 4 cos cubed minus 3 cos. To get tan, or tan is sine on cos, so I can substitute in what we've just found. But I'm not going to substitute in the final lines. I'm going to substitute the first line in where we had a mixture of sine and cos. Because if I want to change these to tan thetas, I'm going to need a mixture of sine and cos, because tan is sine on cos. How do I tidy up this fraction? I look for the highest power, and the highest power is cubed. So I'll divide everything by cos cubed. If I divide everything by cos cubed, then we get nicely sine on cos in each of the terms, and the powers all match up as well. So I can change it now to be 3 tan theta minus tan cubed on 1 minus 3 tan squared. So there's our relationships. Show that x equals cos pi on 9 is a solution to this equation. There's the equation. I've factorized it partially, because I'm going to use the results that we just found. You might not see it straight away, but see, they've given me an idea here where they've told me x equals cos of pi on 9. I know the solution for x is going to be cos of something, so why don't I let x be cos of theta? Now all I have to do is show that theta is pi on 9. If I substitute that in, look what I now have in the parentheses. I've got 4 cos cubed minus 3 cos theta. That's what we just showed cos 3 theta is equal to. And I now have a very simple trig equation to solve. Cos 3 theta is a half. I only want 3 solutions because I'm solving a cubic. So I'll just get the first 3 there. So pi on 3 in the first quadrant, 5 pi on 3 would be in the fourth quadrant. And then to get my next solution, I'll add 2 pi onto my first one there, 7 pi on 3. Divide everything by 3, and I have the 3 possibilities for theta. Remember, we're trying to show x equals cos pi on 9 is a solution. Well, pi on 9 was one of the possibilities for theta. All I required was 3 consecutive because I was solving a cubic. There are the 3 solutions to this equation: cos pi on 9, cos 5 pi on 9, cos 7 pi on 9. So yes, indeed, pi on 9, or cos pi on 9, is a solution to this equation. That's one way you could do it. The other way, because it is a show that, I could just substitute into the equation. And if I substitute into the equation, I'll get 8 cos cubed minus 6 cos. Again, I do that partial factorization, and there's the pattern of cos 3 theta. So the parentheses becomes cos 3 pi on 9. Well, 3 pi on 9, that's the same as pi on 3. That's one of our exact values. Cos of pi on 3 is a half. It does equal 0. So yes, it is a solution. And you might think that second way is probably the more logical way of doing it because it's a show that. But that's why we read ahead in questions. So this would be a question which had parts. And I noticed that the next part is evaluate cos pi on 9, cos 2 pi on 9, cos 5 pi on 9. I'm going to need all the solutions to do this anyway. So I may as well find them in that first part. I now know these are the three solutions, or in other words, the roots of the equation. I'm looking for cos times cos times cos. I've got roots that are in the form cos, cos, and cos. It makes sense to look at the product of the roots because that will create cos times cos times cos. If I look at that equation, it's 1 on 8. So I now know cos pi on 9 times cos 5 pi on 9 times cos 7 pi on 9 is 1 on 8. Not quite what we're trying to work out. We've got the cos pi on 9, we've got the cos 5 pi on 9, we're missing the cos 2 pi on 9. So I need to play around with that cos 7 pi on 9. But if you think about it, cos 7 pi on 9, well hang on, that's in the second quadrant. The acute angle would have been 2 pi on 9. It's the same as negative cos 2 pi on 9. Well, if I substitute that in, I now have my answer. It would end up being negative 1/8. There's our answer for the multiplication of those three cosine terms. These two results are very nice. Z to the power of n plus 1 on z to the power of n and z to the power of n minus 1 on z to the power of n. Two results which we can use. Well, let's go and see what they are. Okay, so z to the power of n using de Moivre's theorem would be cos n theta plus I sine n theta. 1 on z to the power of n would then be cos of negative n theta plus I sine negative n theta. But I could rewrite that as cos n theta minus I sine n theta because I know cos is an even function. So cos negative n theta is the same as cos n theta. Sine is an odd function, so sine negative n theta is the same as negative sine n theta. In fact, I've ended up with the conjugate. I guess the other way I could have came up with the conjugate for that is I've got the reciprocal of z to the power of n, and we know that's the conjugate over the modulus squared. Well, the modulus for our complex number is 1, so it would end up being the conjugate as well. So either way, however we show it, we've got that 1 on z to the power of n is cos n theta minus I sine n theta. So if I add the two together, because I'm adding conjugates, I'll get twice the real part. So it becomes 2 cos n theta. If I was to subtract them, again, because they're conjugates, this time the real part's going to cancel out. I'll end up with 2I sine n theta. I say two results that we can use, unless of course they've asked us to prove those results, but then we'd have to go and prove them. Okay, where is it useful? Well, I could play with this one. If I want to come up with an expression for cos cubed, but I want it in terms of cos some multiples of theta, well, I'll play with z plus 1 on z, because that's the one that's going to create cosine. I want cubed, so I'll cube it. That means on the left hand side, look, I know z plus 1 on z will be the same as 2 cos theta. N's to the power of 1 in that formula. If I cube both sides, on the left hand side I'll get 8 cos cubed theta. That's what we're trying to find, cos cubed. And on the right hand side we get our cubic expansion. But if I group those with the coefficients being the same, so in other words, I'm going to regroup it so it's z cubed plus 1 on z cubed, and then 3 times z plus 1 on z. Then I can go back and use this formula again. So z cubed would be 2 cos 3 theta, and z plus 1 on z is 2 cos theta. It is always 2 times. Don't go and raise 2 to the power of 3 in this case, or multiply by 3. It's always 2 times the cosine, or when we're talking about sine, it's 2I times the sine. Alright, not quite there because we want cos cubed, so divide both sides by 8 and we have a result. Cos cubed is 1/4 cos 3 theta plus 3/4 cos theta. 3b will do us.